Okay, so I'm starting with this question which Somadip has asked me to discuss, which is to do with actually a previous year JEE question. So I'm sure most of you would have seen this question also before. It's a rotational mechanics question, came as a paragraph question a few years back. So in this, what is happening is on a rough surface like this, you have like a combination of two disks which are at slight angle like this because they are having different radii. Okay. So they are connected by a rod rigidly of length. Let's say this is disk A and this is disk B. So this one has radius equal to 2A. This one has radius equal to A. This one has mass equal to M. This one has mass equal to 4M. Okay. And further, this arrangement is such that if you draw this line further, it intersects the rough horizontal surface at the point O, and it is given to us that L is equal to square root of 24A. Now, so the two disks A and B are connected rigidly to a massless rod. Okay, that is this massless rod of length L like this. And now this system is rotating about the axle with an angular speed of omega, let's say like this. Okay. So basically, when you visualize this, what will happen is that each of these discs are in rolling motion on the ground because it's a rough surface. Okay, while the whole thing is going to rotate about this kind of an axis. So they've also mentioned from the origin the vertical axis as the z-axis. The vertical axis has been mentioned as the z-axis. Okay, so various options. Yes. Yeah, Ganesh, I will come to that. Ashwin, I will come to your doubt next only. Okay. So the first thing we have to do is we have to calculate the angular momentum of the system about its center of mass axis. Okay. We have to calculate the angular momentum of this system about the center of mass axis. Okay. So we'll be using a couple of concepts over here. One is that angular momentum about any general point is given by that formula. About any general point is this. Okay. And we'll also be using the fact that angular momentum about the center of mass is nothing but ICM omega. Okay. Yeah, we'll discuss now about angular velocity about the z-axis. So that will come into play only because the question is, based on all these things put together. Just a minute, I will check on the options. Yeah, so for example, one of the options is to calculate the angular momentum about the center of mass axis. The other is the magnitude of the z component of capital L. So what is capital L? Capital L is the angular momentum of the system about the z axis. So they've given in the question that L, capital L, is the angular momentum of the system about the point O. Okay, and then they've asked to calculate what is the z component of that L. Okay, this is the angular momentum of the system about O. So what is the z component of O? That's one of the options. So for that we'll be using this. Okay, so let's start by understanding here that Well, the essential thing to begin with is what is the angular momentum about the center of mass. So I'm just going to simplify the diagram a little bit. So if you take a two-dimensional side view of this, wherein you are seeing the side profile of the two wheels. So you will be seeing the two wheels like this. You'll be seeing the slanted side like this, let's say. Okay. Something like this, let's say. You'll be seeing the two wheels and the axle joining the two wheels center. Let's say this one. Okay. And that thing continued. So this is the side view. Okay, so this point is O. This wheel is of radius A, this wheel is of radius 2A. This length is L, this length is also L. L is given to us as square root of 24A, that was given. Okay, and now this is rotating about this axis with omega like this, such that the omega vector is along this unit vector. Just imagine that when you, sorry, omega is this way. Okay, so the unit vector of omega is along this direction. N cap is the direction of the angular velocity omega. Okay, so you're seeing it spinning this way. Hope that is clear. So when you see it spinning, this point will be coming towards you, this point will be going away from you, like that. So anyway, so first of all, because this disk is of mass 4m, and sorry, this disk is of mass m, and this one is of mass 4m, the system center of mass will be lying here. Okay, and we can figure out what this distance is. This is suppose something, let's say it's, so this is dividing this into 4:1 ratio, so that distance of the center of mass from this point here, this RCM thing, it will be 4/5 of L. Okay, that's just coming from the fact that it's m into 0 plus 4m into L divided by. So the angular momentum about the center of mass, that will be ICM into omega, and the axis of that omega will be the n cap that I have shown. Okay, it's like this. That axis is, let's say, at theta, like this, to the ground, and you can see that theta is such that cos theta, or rather sine theta, is A by L. Oh, sorry, tan theta is A by L, my mistake. So let's just work this distance out here. So this is theta is tan inverse A by L. So that's tan inverse 1 by root 24. You keep this also in mind. Okay. So anyway, so the angular momentum vector is along this about the center of mass. Now moment of inertia of the about the center of mass will be what? Moment of inertia of the first disk plus moment of inertia of the second disk about this axle. So that will be mr square by 2 formula we'll be using. Okay. So this will become 16 plus 1, 17 by 2 ma square. So that is ICM. So actually we need to calculate this first, because we will be using this in the angular momentum formula. So the angular momentum about the center of mass axis will become 17 by 2 ma square omega into that unit vector which I've shown you, which is at an angle theta to the horizontal like this. Okay. So later we will need this thing component of this. We will need the z component of this, where the z axis is clearly shown to us like this vertical axis passing through the point O. So this is our z axis. Now the thing is, we need to calculate the system's angular momentum about this point O. Okay. So the system's angular momentum about the point O. That will be what? RCM cross MVCM plus ICM omega. This thing we need to calculate. Okay. Now we have just seen that ICM omega is this thing. It is this term. Now we need to calculate this term. How much is this term? Angular momentum of the center of mass with respect to that point. So RCM cross MVCM. So this is where the thing gets very interesting. That see what is happening here is that in this diagram, you have to understand what the center of mass is doing. Okay. So if you take a slightly kind of three-dimensional diagram now about the z-axis, you have this two system of wheels. They are doing this, like, this point of contact is going around like this, and this point of contact is going around like this, and the center of mass of the system is also going around like this in a circular path. So Somadeep, you have understood this part. This is the most critical thing. In a three-dimensional diagram, if you view it now, it's like a cone lying on the ground. So imagine a cone lying on the ground. How it would go, these points would all describe circles like this. Now imagine you got a frustum of a cone on the ground. So that whole thing would go in circular path around this. This is clear, Somadeep? Yeah, I mean, obviously you've understood this because you're asking the angular velocity about the z-axis. So this point is clear. Okay. So now you can see that the velocity of this point, okay, disk A is center, and the velocity of disk B is center. So the disk A is rolling on the ground. Okay, so if you see the side view of disk A now, its center is going like this, and about the center it's got omega like this. So this point is not slipping. So the center of disk A is equal to A omega. The center of disk A is moving at a speed of A omega. Similarly, the center of disk B is moving at a speed of 2A omega. Okay. Now, if you pay attention, okay, this point of contact here now, it is describing a circle. The point of contact of disk A is describing a circle around on the horizontal plane with the z-axis as the axis. Okay. So that circle is of radius how much? That circle is of radius this much in this diagram. This radius RA. Okay. So the point of contact of the disk A is describing the circle of radius RA that is in this diagram. So if this point is clear, RA is the radius of the circular motion of A's point of contact. So that radius we can get from this now. So that radius RA will be square root of L square minus A square. And remember, L was given to us as root 24A. Sorry, L square plus A square is the hypotenuse. So that is becoming 24 plus 1 square root A square. So that's becoming 5A. Right? So similarly, you can see the radius of the point of contact of B. Okay, so they are like what? RA is equal to 5A and RB will accordingly become 10A. Okay. So now you see these disks now, their linear speed in the circular motion, they are doing UCM with a linear speed which we know, which is A omega for this one and 2A omega for this one. And Okay, so their centers are doing a linear motion. Sorry, the linear velocities of their centers are this much in magnitude, and the radius of the circular path of the point of contact is this much. Okay, so if we say that the system about the z-axis has an angular speed omega prime, okay, so that omega prime should become what? It should become the linear speed of the disk A divided by its radius, which will be equal to the linear speed of the disk B divided by its radius, which will incidentally be also the linear speed of the center of mass divided by its radius. Okay. So we'll come to that later. So this omega prime, therefore you can see, is becoming omega by 5. That's how we are getting that the angular speed of the system by L cos theta क्यों divide करेंगे बेटा? See, we are looking at the point of contact now. The point of contact is describing a circle of how much radius? 5a, na? On the surface, if this is the disk A, the point of contact is describing a circle like this of radius 5a now. No, but then see, the problem is the disk is slanted. See, when you see from the side view, now the disk is slanted like this. Okay. Now, where from we are getting the condition that this point is not slipping, that the linear velocity of this point and the backward velocity because of the angular velocity, with respect to center of mass, they are related by the relation V is equal to R omega. You understanding? The disk is slanted now. So we have to pay attention to the constraint relation for no slipping at the point of contact and understand the circular path that the point of contact is describing now. You see, geometrically, it is after all what? It's how this point is moving from point to point, theta. So if, for example, this point completes a circle in time period t prime, okay, then my omega prime is equal to 2 pi upon t prime. Now, in that time t prime, how much distance this thing has completed? It has completed a distance of one circumference, which is 2 pi Ra, and that should be equal to what? The linear speed of this point, which is the same thing as a omega. Okay, so actually it is a little bit more complex. No. So see, whether you are seeing the angular position of the point of contact with respect to the z-axis, or you're seeing the angular position of the center of mass of the disk A with respect to z-axis, or you're seeing the angular position of center of mass of disk B with respect to the center of mass, with respect to the z-axis, all of them have a common value of omega prime. But what you have to understand is that this VA is equal to R omega A. This VA is actually not exactly the center of mass of A's velocity. It is like at that point of contact of the disk, the forward velocity of the translate because of the translation and the backward velocity because of the R omega, they are cancelling each other. You understanding? Or forget about VA. Don't think of it like this. What is happening is that this is spinning at an angular speed and not slipping. No? So the point A has a linear speed in the forward direction with respect to the ground. The point of contact A has a linear speed of how much? A omega, no? Because it's not slipping. you have to understand that the circle that the center of mass is describing is slightly different compared to the circle that the point of contact is describing. Yeah, that is the thing which is a little confusing. So, think of it like a simple geometrical constraint instead of so much. Just imagine that this disk, its plane is like this. Its plane is not perpendicular to the plane of contact. Okay. Now just focus on this point. So if this is spinning about this axis with an angular speed omega like this, okay, or an angular speed whatever, omega like this. So this point has a speed going into the plane which is a omega, no? So its forward linear speed should balance that so that it does not slip. So this point of contact on the ground, this is describing that circular path with what kind of speed? The speed of that point A is equal to a omega. Is it clear now, Samadhi? So if this is moving with a speed like this and is moving in a circle of radius Ra, its time period for this circular motion about the z-axis, that time period will become how much? It will become 2 pi Ra divided by Va. So that time period will become 2 pi into 5A divided by A omega. So that therefore you can see that the omega prime, which is 2 pi upon that time period, is omega by 5. Yes, it's the point of contact whose linear speed is a omega and whose speed with respect to the center of mass is minus a omega. Okay. So with that, now we can see that, okay, so once that point is clear that the system has an angular speed of omega prime with respect to the z-axis. Okay. So that omega prime was in which direction? V in this direction, the V of the center of mass was coming out of the plane. Okay. So the center of mass is somewhere here. So it has a velocity vector coming out of the plane, VCM like this. Okay. And about this, it has an angular velocity omega prime, which was omega by 5. So now you can see that you can figure out the VCM because this center of mass is describing a circle of this kind of radius, let's say D or capital R or whatever. It's describing a circle of this kind of radius. So this VCM's magnitude will become the radius of the center of mass with respect to the z-axis into the angular speed of the system about the z-axis. Okay, just like this point, its velocity is, it's like VA is equal to omega prime into RA. Okay, VB is like that, omega prime into RB. So we have the relation A omega is equal to omega prime into 5A. Like that, we have the relation that 2A omega is equal to omega prime into 10A. So like that, now we have the relation that VCM is now this one you'll see is becoming, so this was L and this we had just seen was 4L by 5. So my capital RCM will become L plus 4L by 5 cos theta. So that will become 9 by 5 L, and cos theta was L by Rn. So that was nothing but root 24 by 5. So this will actually become 9 by 5 into L itself, which is root 24a, into root 24 by 5. So this is RCM. Okay. So VCM, velocity of the center of mass, is becoming 9 by 25 into 24 A omega. In terms of A omega. Otherwise, you can write it in terms of L omega also. It's fine. Now, once we know the VCM, what we will do is we'll calculate the angular momentum by using that formula. So the angular momentum about the point O will become, so with respect to the point O, your center of mass is lying here. So it has a position vector which is like this. Okay. And it has a velocity vector which is coming out of the plane. So I'll show it with the dot. Okay. So these two are actually perpendicular to each other. So this term RCM cross MVCM, it will actually have a magnitude of, so this vector will be like this. This will be your RCM cross MVCM. We can write this as the angular momentum of the center of mass about the point O. We can write it like this. Okay. So you can do the cross product and see it's like this. Okay. So this term will just become RCM, which is again L plus L by 5, okay, into total mass, which is 5m, into VCM, which we just calculated from here, which was 9 into 24 by 25 A omega. So this is 9L by 5 into 5m, okay, into 9 into 24 by 25 A omega. Okay, so this term, angular momentum of the center of mass about the point O, this has now got a magnitude and direction. You can see it's along this direction. If this angle is theta, then here this angle is theta. So it's got a magnitude of 9 by 5 into 9. Now L also you'll have to substitute as root 24. Okay. Just I think we are missing some term over here. Just let me check. So VCM was 9L by 5 into this cos theta term, that is root 24 by 5, okay, into omega, which was omega prime by 5. Sorry, omega prime. Sorry, that is the term I missed. This was omega prime. Okay. So that will be another omega by 5. Okay, because remember omega prime is equal to omega by 5 from here. So this RCM here is 9 by 25 into 24A. So that into omega prime. So that becomes 9 into 24 by 125 A omega. Okay. So this is omega prime, but if you substitute it as omega, you also have another 5 in the denominator. So it becomes omega prime by, rather omega prime becomes omega by 5. So this becomes by 125. Right. So this becomes 81 into 5 cancels out. So 81 into 24 by 125 into M A L omega. And then again you substitute L as, again you substitute A as root 24. I mean L as root 24A. So you'll get this sort of a term. 81 into 24 root 24 by 125. M omega A square. This is this term, the magnitude of the angular momentum of the center of mass with respect to the point O. Now this is not our total angular momentum, because we also have the other thing. We have the ICM omega, the angular momentum of the rigid body about the center of mass. We still have that. Okay. So this is just this term, RCM cross MVCM. So now the total angular momentum vector now. So Somadeep, you are clear up to this step now? Yeah, you had the confusion only in omega prime now, how we got that. So now things should be clear for you. So now the total angular momentum of the system about this point O, that should be this now, RCM cross MVCM plus ICM omega. So this is the term we have written as angular momentum of the center of mass about the point O. And this we can write as the angular momentum about the body about its center of mass. We can write it like this, okay? So you can see that with respect to our z axis, and this was the axis along which that rod was at an angle theta, this term we just now saw was like this. This term was like this. So this angle was theta. So it had a magnitude of that complicated thing, 81 into 24 root 24 by 125 m omega a square. This was this term. Okay. Now the other term we had seen earlier, that was this term. Yes, so now the other term we had seen earlier, the angular momentum about the center of mass. We had seen that earlier. So that is this vector. That is this vector here, which is along this unit vector. So 17 by 2. Okay, 17 by 2 ma square along this vector. So that's this other term. So this is the angular momentum of the body about its center of mass. So that is 17 by 2 m omega a square in magnitude. So the net angular momentum is the vector sum of these two things. Now we have to find the net angular momentum's z component. So the net angular momentum z component is going to be this one z component plus this one z component. So this one z component will be plus 17 by 2 ma square omega sine theta, and this one has a negative z component of minus 81 into 24 root 24 by 125 ma square omega cos theta. And we've seen earlier that that triangle was like this. Theta was such that this was root 24a, This was A and this was 5A. So you can substitute these things. So 17 by 2 into sine theta, that is this, minus 81 into 24 root 24 by 125 into cos theta. So cos theta is root 24 by 5. You get this huge kind of number to ma square omega. So this will become 17 by 10 minus 81 into 24 square, okay, divided by 125 into 5. So that is 625. This kind of term into ma square omega. Okay, so definitely this is not that 55 ma square term. It is a bit different from that. Okay, if you calculate its estimated value, so actually the actual angular momentum will be along the negative z axis, approximately. So it comes close to about 73 ma square omega. This kind of term it comes to. This is the z component of the angular momentum. Okay, so hope this is clear, people. Okay, next I'm moving on to one of the questions which Ashwin has sent. Yeah. So one question we were already doing last time and another one I have not managed to pick up. So we'll start with that since we are in mechanics. We'll pick up the mechanics question Ashwin had sent earlier. Then we'll come back to the other question. So it said that on the edge of the table, you have a rod such that only a very small part of it is outside the edge. A negligible part of it is outside the edge. Okay. So you have a thin uniform kind of rod which is lying on a table like this, such that it's more or less on the table, just a very small portion is outside. Right. So this is a rod of mass m, and let's say its length is L. Now what we are doing is we are applying a sharp impulse to this end. Okay. We are applying a sharp impulse. Okay, Aditya. Yeah, I've got your doubts. Right. This was the question, Ashwin. I mean, you did not send the diagram of the question. I don't think the diagram was there also. I don't know. But I'll just share the question with you people. But this is what I made of the question anyway. Yeah, there was no diagram in the question anyway. So now we have to find the this thing, maximum height of the center of mass or something. Let me check. So we are applying an impulse such that that kind of jumps up, that rod kind of makes a vertical projection kind of thing. Okay. So a uniform thin wooden plank AB of length L mass M is kept on the table with end B slightly outside. When an impulse J is given to the end B, the plank moves up with the center of mass rising a distance h from the surface of the table. Okay. So this, the center of mass now rises a distance h, okay, above. So we have to find the value of h. I mean, the possibility of h. H can be greater than something, h can be less than something. All this we have to calculate. Okay, so various options are given. Just give me a moment. I'll try to share the question. Not able to. Yeah, I think I can share the question now. Yeah, so this is the question. Just go through it. I'll explain. Okay, so you can see the options. I've explained the question in the diagram. This is how I am interpreting the diagram. Okay, so let me go back to my whiteboard. I'll explain. So see, the thing is that here we have to understand what kind of impulse the table will apply through reaction. So to understand that impulse that the table will apply through reaction, you have to figure out like this, that see, if you had in gravity free space a rod like this, which was at rest initially, and you just applied an impulse at this point, what would happen? This rod would develop a VCM and an omega about the center of mass such that VCM would be J by M and omega would be equal to this thing, J into L by 2 divided by ml square by 12. So it would be 6J by ml. So you would see that this point here, this corner point, would have a very strong downward velocity. It would have a velocity like this of omega L by 2 minus VCM. So you can see that omega L by 2 is 3 times J by M. So it would be 3 times minus 1 of J by M. So this would be in gravity free space. So that means the moment you apply this over here, there's a tendency of this point to push against the ground. Understanding, Ashwin? So what I will assume is that the ground, I mean, there will be impulse forces acting in such a way that this corner point is where the contact actually happens with the ground. I mean, normal reaction is balancing weight, but the moment you apply the sharp impulse, there's a sharp impulse from the ground that is acting on it. No? So it's almost like, if you imagine the rod is like this against the ground. So this point pushes against the ground because of this VP. So the ground reacts by applying an impulse like this, some reaction impulse, let's say J prime like this. Okay, so that is the concept we have to apply. So the moment you apply this impulse, the ground will react by applying an impulse through this corner point J prime. And as a result of that, what should happen? If it is an inelastic impact, this will remain at contact. Whereas if it is an elastic impact, then there will be, maximum, there'll be zero loss of kinetic energy or whatever. So we'll come to the elastic thing later, but the minimum velocity that you will get, the minimum kinetic energy of the system that you will get is when it is an inelastic impact. So if it is an inelastic impact, what should happen? This point of contact over here should remain in contact with the ground just after this impulse is applied. So what should happen is just after the application of impulse, the center of mass has a velocity VCM, and about the center of mass there is omega. So this point cannot have a negative velocity. It can have a positive velocity like this, but it cannot have a negative velocity, depending on whether it's jumping up from the ground or it's making it sort of inelastic kind of situation. So this point is still in contact while the center of mass is going up. You understanding? So the result of this impulse picture now should be this, where what I'm showing as Vp should be greater than equal to 0. So Vp equal to 0 will correspond to the minimum value of VCM, because it corresponds to the minimum kinetic energy. Okay, so that corresponds to the minimum value of H that you will get for the center of mass. So if we take Vp equal to 0, what is our condition here? That VCM should be equal to omega L by 2. That's one. Okay, then we have J plus J prime is equal to M VCM. Okay, and we have J minus J prime into L by 2 is equal to ICM omega. So you solve this system of equations and you'll get some VCM. In terms of J and M, you'll get some VCM. Okay, and then your H max will be VCM square by 2G. Because once it loses contact with that surface, the angular speed will remain contact, and it's just vertical motion of the center of mass, that kind of situation. Okay, so just complete this, all of you, and that will give you the lower limit. Okay, now the upper limit we'll have to think about. Okay, because this is assuming E is equal to 0 when it sort of, it's like you thump this over here, so this thumps against the ground, so there is some kind of collision impulse. J prime is like an impact force, it's like an impact impulse. So it can be a situation where it's elastic, it can be a situation where it's inelastic, that kind of situation. So the minimum energy, kinetic energy, is transferred to the center of mass and about the center of mass in the situation where it's inelastic. So we are taking that. Okay, so just let's look at the solving part of this. So this equation will become j minus j prime is equal to ml square by 12 divided by L by 2 into omega, which from here you can substitute as 2 VCM by L. So this will become j minus j prime will become 4 by 12. So 1 by 3 now. Are we getting this? Okay. Now compare it with the second equation. So we have 2 times j is equal to 1 by 3 plus 1 or 4 by 3 MVCM. So this will give us the condition that VCM will become 4 by 3. So 2 divided by 4 by 3. So that will be 3 by 2 j by m. Okay. So your H max from this case will be 3 by 2 j by m whole square by 2g. So 9 by 8 j square by m square g. So this will give you the H max for this case. So this is when E is equal to 0. So when E is greater than 0, this H max will be more than this. So in general, your maximum height of the center of mass should be greater than equal to 9 by 8 j square by m square g. Okay. Now the other side, the condition will come when we take the E equal to 1 case. This is when we have taken the E equal to 0 case. So just Oh, sorry. Yeah, my system had got muted. My mistake. Yeah. So, Ashwin, coming back to this now, why we are putting this as the minimum condition is that this is the situation where the collision is. This is the situation where the impact impulse that is acting from the horizontal surface now is such that it's creating a E equal to 0 kind of condition. It's creating an inelastic condition. So that's why this is the minimum case. Okay, this is when there is maximum loss of kinetic energy due to the collision impulse J prime by the surface. I might ask that there is no collision. It was already at rest on the surface. So how come there's a collision? So that's where you have to visualize now, that think of this like something happening in slow motion. Okay. So imagine this situation I was trying to tell you, but I was unfortunately muted. Just a second. Yeah. So try to think of this situation where before you applied this impulse now, before we applied this impulse, what was happening? Normal reaction and weight were balancing each other. So as far as the net force on this body is concerned, it's as good as it being in gravity-free space, no? Because the gravitational pull on it is balanced by some other force. So had it been in gravity-free space also, it would have been in the same situation. So had it been in gravity-free space and we have applied this kind of an impulse on it, what would happen? In gravity-free space, if we applied an external impulse, this is what would have happened. The center of mass would have jumped up with a velocity, and about the center of mass there would be an omega like this. So VCM would have been J by M, less than that case over there, and omega would be such that it would be J into L by 2 divided by ml square by 12. So we just saw that this would be 6J by ml. Now this would be my omega. So this point would be hitting against the ground with an instant, would be having an instantaneous downward velocity. So this point was A. So VA would have in fact a downward velocity of 2 times VCM, and this would have an upward velocity of 4 times VCM, like this. This is what would happen. But here what is happening? It's against the table. So the table immediately reacts by applying an impulse at this end. So after we apply this impulse, the table applies like a collision impulse. This is like an impact force into time. So this J prime is like a reaction impulse. This is like a collision impulse. Okay. So we solved J prime for the situation where this point of contact should be at rest. So for Vp equal to 0, that means the coefficient of restitution is 0. But we can also solve for J prime for the situation where E is equal to 1. So if E is equal to 1, this will be maximum. Maximum impulse is acting on it. And there will be maximum kinetic energy for the system. So there will be maximum height to which the center of mass climbs. Understanding? So we will think of it like, suppose this was a soft rubber rod. So you could think of the two impulses acting in slow motion, one after the other. First, the impulse J acts on it. That gives it this kind of a situation. Okay. So already you can see that after the impulse J has acted on it, this is what has happened. The center of mass has got that velocity which I've written above, J by M, is got the omega about this which I've written above. Okay. And this point, E or whatever, this has got this downward velocity of this thing. It would have got a velocity of, how much is that now? 2 times VC. Now what will happen is that the second impulse will act on it. And the second impulse will act in such a way that as a result of this impulse, now the center of mass has a different velocity, let's say VCM prime, And about the center of mass, it has now developed this kind of a velocity, this kind of an angular velocity, omega prime, such that this point should now have a separation velocity. Here it was having an approach velocity. Okay, so we should have E equal to 1 means V separation should be equal to V approach. So V separation will in this diagram become how much? It will become VCM prime plus omega prime L by 2. And this should be equal to, in this diagram, what it was, which was this VA was coming from this calculation. It was omega L by 2 minus VCM. Then we substituted this, so it came out to be like this, 2 VCM downwards. So 2 VCM, which is basically 2 times J by M. So this condition will tell us how much impulse this applies. And from that, we will know how much this VCM prime is. And from that, we will know how high it will climb. So this time when it makes that inelastic collision, what happens is, or that inelastic kind of impulse acts on it, the moment you apply this, you will see that this and this act back to back. But as a result of this and this acting, the rod will go up such that it has such a strong omega that it's spinning the other way. Are you following, Ashwin? Okay, so you have to now solve this using the unknown quantity J prime now. So between this diagram, this one, and this diagram, you have to again apply impulse momentum. But what is the impulse now? It is J prime. Now, this has already acted to give it this. This J has already acted. So you're dividing the two impulses which are acting back to back almost simultaneously, but into two events. So first on the rod, this J acts and gives it this kind of a motion. And immediately then J prime acts and it changes the motion from this diagram to this diagram. Okay, so now we'll have a new set of equations that J prime is equal to M VCM prime minus VCM, okay, or J prime plus M VCM is equal to M VCM prime. So J prime plus J obviously is equal to M VCM prime. This is your first constraint relation. And J prime into L by 2 will be equal to I omega prime minus, now that was in the opposite direction. So you'll have to write it as minus I omega. Because this is now, originally it was like this. So this will actually become J prime minus J into L by 2 is equal to ml square by 12 omega prime. When you compare with this original equation, this one, from where we had got this value actually, that omega is 6 J by ml. from where we got this. Okay, you'll get this. Okay. So now you have to solve this system of three equations for this constraint relation. For this constraint relation, that BCM prime plus omega prime L by 2 should be equal to 2J by M. So to solve for this constraint relation, from that you will get your VCM prime. So you get VCM prime is how much? So then your H will be VCM prime square by 2 G. And from that you will get that upper limit of H. The lower limit was what we calculated earlier. It was that 9 by 8 factor, na? J square by M square. From this you'll get the upper limit factor. Okay, Ashwin, understood this question now? Okay, so I think you can complete it from this point, the calculation part. Okay, so I'm moving on to the other inductance question which we had sent. That superconductor thing which had an inductance. Yeah, so just go through this once more. We will discuss calculation in this. Okay, so let's come to this question. So first thing we have to do is we have to find the flux through the ring as a function of its z coordinate, no? And in its initial z coordinate was the was 0, right? Let's see how much we can do over here itself. So the z component of magnetic field is what will create this thing on it, no? will create flux. The magnetic flux through the ring will be integration of Bz into dA. Screen is not shared. The question is shared now, no? Oh, sorry. Are you able to see the question now? Is it shared? Okay. So in this this ring situation, you can see that what is happening is through the circular ring, the Z component of magnetic field is the one which is creating flux. Okay. Whereas the radial component of field is not creating flux, but later we will see that it's going to create force. It's going to create magnetic force when there is induced current. So B naught, A, beta, these all constants. Z is the vertical and R is the radial position of the coordinates. There's no current flowing in it initially. It released from rest from the point Z equal to 0. And the center of the ring is at the point R equal to 0. Okay. So let's go to transfer this information. So Z component of field was something like this. It was B naught into 1 minus AZ or alpha Z. And the radial component of field is B naught into beta R. Okay. And what all other information is given starts from Z equal to 0. Okay. So I'm just moving away from this screen, moving to my whiteboard now. Okay, so this situation. So what is happening is that this is where the ring started from, where the center of the ring was Z equal to 0, R equal to 0. It started from rest. Okay. Now after some time, let's say the ring has come here. It has a downward velocity V. Okay. That's some time t. So as a result of that, what is happening? The magnetic flux through it will be, what will happen to the magnetic flux? It will increase or decrease. It will tend to increase the magnetic flux because Z is a negative quantity now. So it is at some Z equal to minus Z, because this was the coordinate Z equal to 0. Z axis is upwards. Okay. So it has a stronger flux through it here compared to the flux through it over here. So anyway, the magnetic flux is going to be this B dot dA integration. But when you do this B dot dA integration, you will be left with Z component of field integrated over the area vector. And the Z component of field is not varying with the radial direction. It's only varying with the Z. So it's going to be B naught 1 minus alpha Z into pi, what is given about the radius of this one. The radius of the ring is R naught. So the ring has mass M, radius R naught. Okay. So pi R naught square. This is the magnetic flux. Right, Desmond? And in this you can see that your dz by dt is actually minus V. Why minus V? Because V is in the direction of negative Z axis. So induced EMF which will be of magnitude d phi by dt, but in general is minus d phi v by dt. So what I've done is I've taken the area vector upwards because the magnetic field vector is also upwards, the Z component. So I've taken the area vector upward. So my upward direction is positive. So if I get something as positive, it should be anti-clockwise as seen from above. If I get something as negative, it should be clockwise as seen from above. Okay. So this will become minus of B naught pi R naught square into differentiation of 1 minus alpha z. So P naught pi R naught square dz by dt. They should be E induced. Okay. But dz by dt is minus v. So this will become minus P naught pi R square v, where v is in the downward direction. Which means that, as it makes sense, that when I'm seeing from above, I'll see a clockwise current, because the magnetic flux coming out of the plane will be increasing. So when I see this from above, what I'll be seeing is this, that the z component of magnetic field is coming out of the plane. This is the z component of magnetic field, and that is increasing. So to counter that, there will be a clockwise current. Okay. And then of course, along with that, there is also radial component of field. So there is this radial component of field at every point. And that radial component of field is given by how much? It is given by B naught into beta R. So this I dl cross B is creating an upward force. Okay. So first of all, the loop equation for this ring will be, now remember, the ring has zero resistance. The ring also has the property of superconductance. So its resistance is zero, or its conductivity is tending to infinity, but it has inductance equal to capital L. Okay. So for this loop, the equation becomes E induced minus L di by dt is equal to 0. So E induced is, okay, now E induced is in the clockwise direction. So we'll just take it as in magnitude, and current is also in the clockwise direction. So this will become B naught pi R naught square V plus L di by dt is equal to 0. This is the KVL equation, loop equation. So Ashwin, this is clear now? Okay. And now along with this, you can see that any length element on the loop which is carrying clockwise current. So any length element IDL like this, or any current element IDL, will experience, because of magnetic field's radial component, it will experience a force coming out of the plane. So it will experience a DF coming out of the plane like this. So that magnetic force coming out of the plane will be IDL into B's radial component. So the net magnetic force will become I into radial component into 2 pi R naught. And the radial component will be how much? It will be B naught into beta R naught into 2 pi R. So this is clear, Ashwin? Alpha term in the EMF I have missed. Yeah, I have missed the alpha term, correct. Where is it now? There will be alpha dz by dt. Yeah. Just make a correction here. There is also an alpha over here. right? So radial part is clear, na? So now see what is happening. If I draw the three-dimensional diagram again of the loop, gravity pointing downwards, as it's having a downward velocity, it's experiencing magnetic force in the upward direction and gravitational force in the downward direction. So its equation of motion becomes like this, that mg minus magnetic force is dv by dt. Mg minus magnetic force is m dv by dt. So when you substitute this, this is mg minus, again it will become that kind of term, p naught beta pi r naught square 2, this kind of term into I is equal to m dv by dt. So you can see you have that coupled differential equation kind of thing. You have here L di by dt is equal to b naught pi r naught square alpha into v. Okay, this is your first equation. And here you have m dv by dt is equal to mg minus 2 b naught b pi r square beta into I. Okay. So now you should be able to proceed from here. So what you do is you differentiate the second equation with respect to time. Do differentiation of the second equation and substitute di by dt from equation 1 and see what you get. And from there you proceed further. Okay, so you'll get your equation of SHM and all. Yes, Ashwin. So here you're getting m d2v by dt square is equal to minus of 2 beta pi r naught square v naught into di by dt. And then you plug in this value. So that becomes minus of 2 b naught square pi square r naught to the power 4 alpha beta upon L v. Okay, so bring this m also on this side. So your d2v by dt square becomes like this. So your v will become a sine omega t plus phi, where you understand that omega is b naught pi r naught square into square root of 2 alpha beta by ml, something like this. Okay. And at t equal to 0, your v was 0. Started from rest. So that means sine phi should be 0. So mostly we'll take phi as, an acceleration was positive in the downward direction. So we will take phi as 0 instead of pi. So your v will actually be a sine omega t plus phi. Sorry, a sine omega t And then we'll use the fact that at t equal to 0, the downward acceleration was g. So the acceleration at t equal to 0, dv by dt at t equal to 0 should be a omega, and that should be equal to g. So from that you will get the a also, the amplitude of the v. Okay. Now once you got v like this, now you can see that what about your displacement? So ds by dt is a sine omega t, where the displacement is s in the downward direction. So sine omega t dt integrated from 0 to t will give you 1 minus cos omega t. So the maximum displacement it will undergo is 2 times a by omega, where a you have calculated from here. A is equal to g by omega. So these kind of terms and all. So Ashwin, I think this should be okay now, right? You can finish off the question, handle it yourself, right? Okay, very good. So I'm going to switch to some more questions. Give me a moment. Bhumik, I will come to your question also. What will be the condition for equilibrium? Just let me check, Ashwin. हाँ, वर्टिकल कोऑर्डिनेट फॉर द इक्विलिब्रियम यू कैन सी ना. सो वहां पे देखो क्या हो रहा है ना, इक्विलिब्रियम किस पोजीशन पे था जब ए इज 0 ना, एक्सेलरेशन इज 0. सो यू हैव गॉट v एज कैपिटल A sin omega t ना. So acceleration will be 0 when cos omega t is 0. Understanding, Ashwin? So you will get that as when the phase is pi by 2 kind of thing. Na? So in that you had written s as a function of t. Na? So in that you can substitute that thing, the phase thing. So here you see your v is a sin omega t. So your acceleration is a omega cos omega t. So for your acceleration to be 0, your omega t has to be pi by 2. Okay. And now you'd see last step, your displacement here, this one was a by omega 1 minus cos omega t. So the condition for this is that, so s is equal to a by omega when acceleration is 0. That is the equilibrium condition. So you can see the oscillation is happening between s equal to 0 and s equal to 2 times a by omega, and the mean position is in between. Okay, this is where the acceleration is 0. But in this case, it's just that remember a is a velocity amplitude. A is not a displacement amplitude. And that is why this thing is actually the displacement amplitude. The displacement amplitude is actually a by omega, because capital A is the velocity amplitude of the SHM that we've written. Okay, good. Yeah, so just switching over to some more doubts next. So Aditya has also sent some doubts, and a couple of doubts of Shreya are also pending. And then more people have sent doubts today also. So I'm going to try and cover as much as I can. Okay, let's start with this question, EMI type of question. So I think it's important all of us discuss this. So I'm just sharing the question. Again, it's an induction type of question. Time varying magnetic field. So non-conservative, non-electrostatic electric field, that concept. Okay, so I'm switching to my screen. So the main trick in a question like this is that whenever you have a cylindrical region where the magnetic field is symmetrical, it has at least radial symmetry, even if it is not uniform. At least it should have radial symmetry, and our magnetic field is varying with time. So in that situation, you know that your electric field lines are circular loops. Okay, you have those concentric circular loops as electric field. So make use of that effectively. So I'll tell you how to make use of that. If you take a radial metallic line, an imaginary or real radial metallic line, the induced EMF along that line will be 0. Okay, so this magnetic field is such that it's increasing at the rate of 2 Tesla per second. Okay, now we've got this kind of square frame here in which we have to find the induced electric field and all, sorry, the induced voltage and all. Okay, so this is the center of the side AB coincides with the center of the magnetic field. 20 centimeter loop. Okay, square loop, non-conducting and all. Okay, so if the center of the cylindrical region or the disk over here is O, you know that for magnetic field going into the plane which is increasing, we'll get anti-clockwise circular electric field lines. Okay, like this. The electric field lines will be like this. Okay. So generally in this kind of a region, so see, generally in this kind of region, I'll tell you a trick that we are having these circular field lines. Now suppose we just want to find the potential difference across any arbitrary rod like this, or any arbitrary path, straight line path from P to Q. So to do that, what you do is you just join the center with these two. Okay, so now you think of this imaginary area. Okay, so the total induced EMF in the loop POQ P, that is equal to that area into dB by dt. Okay, so this will be the voltage difference across OP plus PQ plus QO. Actually, you should not call it voltage difference because the term voltage generally refers to, you can call it the potential difference, it's fine. It refers to conservative field, but we know here that we are dealing with non-conservative. So this thing is equal to that area of the triangle POQ into dB by dt. Okay. Now what will happen here? These two will be 0. This term and this term will be 0. So this only will become that area of the triangle into dB by dt. Why these two will be 0? Because see, at any point on this line, your E vector is like this. Okay, and your DL vector is like this. So E dot DL, that is only that potential difference now. So that will become 0. Is this point clear, Aditya? Okay. So for example, in this question, what all we want to do? We want to find the magnitude of the line integral of induced electric field along the path BC. So for the path BC, what you do is you just join this with an imaginary line. So you take this triangle. So for the triangle OCB, the rate of change of flux is area into dV by dt. So area of that triangle will be, if the side of the square is L by L, it will be half into height, that is L by 2 into base, which is L. So L square by 4 into dV by dt. Okay. So the induced voltage in the loop OCBO, this one will be L square by 4 into 2 Tesla per second, which we got here, dV by dt. So now you can see that this will be E dot dl integrated from O to C, then C to B, then B to O. So these three terms is the net induced EMF in the loop, and that is equal to your 20 centimeters whole square by 4 into 2 Tesla per second. Okay, so here this term will be 0 and this term will be 0. So ultimately your line integral of E dot dl across BC, its magnitude will be this much. Okay, similarly you can do for the other parts also, CD and all that. Is the question clear, Aditya? Okay, very good. Let's move on to another question. Can anybody tell me what is the concept used to solve this question? The current in the resistor just after the switch is opened. See, just after the switch is opened, you're not getting a discharging circuit or anything. It's just that the circuit is broken. So at that moment, how much should the current be? And what is the reason behind that? Yeah, Aditya, I'll discuss. Anybody else has an answer for this? Yes, very good, Samir. So what is that principle actually called? The one you are referring to? It's a principle called conservation of flux. Magnetic flux cannot be suddenly created or destroyed. Energy can be dissipated very fast, that's okay. because there can be a very high transient current to dissipate energy through the resistor and all that. Okay, but magnetic flux cannot be suddenly created or destroyed. So there's a principle, a universal principle called conservation of flux. So that is what is applicable in a situation like this. Yeah, so the principle we use in a situation like this, it is called conservation of flux. Okay, I'll give you another example of a question, then we'll come back to this one. So supposing we had this situation. And we have a two-way switch over here. This is position 2, this is position 1. So let's say given E is equal to 20 volts, R is equal to 10 ohms, L1 is equal to 5 millihenry, and L2 is, let's say, 10 millihenry. Okay. Now the switch S is in position 1 for a long time. Okay. Now it is switched to position 2. So find, in fact, let's take this also as R1. This is R2. So R1 is this much, and let's say R2 is also just happens to be the same. So it doesn't matter whatever R2 is. So find the current in R2 just after S is switched from one position to other. Okay. Just after the switch S is switched from position 1 to position 2, what will be the current in the resistor R2? So here also we will use this conservation of magnetic flux concept. So what is happening when the above circuit, let's say this is circuit A, okay, and this is circuit B. So when the switch S is in position 1 for a long time, so that means circuit A is in steady state. So that point of time, there is this current, let's say I naught. Okay. So I naught, as you know, will be E by R1. So that will be 2 amperes. Okay. Now what we do is the switch is switched from 1 to 2. Okay. And immediately after that, okay, let's say the current is I1. So I switch this to this position. So what happens immediately after switching it to this position? Okay. Now this current changes to some I1 in this loop. So this I1 will undergo a sudden change, because what can happen now, the EMF can undergo a sudden change. but dissipation of energy can happen suddenly because there's a strong, transient current, but flux can neither be created nor destroyed. So what was the magnetic flux in the system at this point of time? The magnetic flux was equal to L1 I naught, right? Because EMF induced is equal to rate of change of flux. So that is this thing. So from that you can see that for any solenoid, for example, the inductance is equal to mu naught into number of turns into pi r square into L now. So the magnetic flux is Li. The EMF induced is minus L di by dt. Okay. And just after changing the switch, what is the magnetic flux? It is becoming L1 plus L2 into I1 in this diagram, because there's a current I1, common current I1 through both the inductors. You understanding? So conservation of flux will tell us that L1 I naught will be equal to L1 plus L2 into I1. The current in this branch will undergo a sudden change, and there's no problem with it undergoing a sudden change because the rate of change of current is so sharp that the inductor provides the voltage required for that current to undergo a sharp change. And you will also see that there's sudden loss of energy. If you calculate the total magnetic energy stored in the inductor first, half L1 I naught square, and after calculation of this I1, you calculate the energy stored now, that is half L1 plus L2 into I1 square, you see there's a drop in energy. But that drop in energy is getting dissipated through the resistor immediately because there's a strong sudden change of current. So there's a transient amount of power dissipated. But what will remain conserved is the magnetic flux just from the moment before to the moment after. Magnetic flux can only undergo a gradual change. You're understanding this point? So this current, so I had taken the inductances 5 and 10. So 5 I naught will become 15 I1. So the current will suddenly drop to I naught by 3 or 2 by 3 amperes. Okay. And thereafter, of course, it is a inductive circuit with time constant L1 plus L2 by R. Okay. So that current as a function of time will become I1 into e raised power minus t by tau. It's a decay of current. It's a discharging circuit. It's an energy discharging circuit. No, so it's changing from this thing, I1, because see, immediately when you switch the position of S from S1 from position 1 to 2, the current in the circuit changed from I naught to I1. So that's why here this I1 will be 2 by 3 amperes. And this time constant will be this value. Understood. So now the same reason why, Aditya, that question you had sent me earlier. Okay. Now here see, for flux conservation, what has to happen? The current through the inductor has to remain the same. So there's no second inductor involved. So the current will remain the same as it was, E by R only before. So this factor X should be 4 over here, because the current should be E by R just at that moment. Okay, hope this is clear. Now let's try out this question next. So in this, you just use that formula now to understand the relationship between power. Okay. It is this, no? So you can see that the power versus frequency like this. This will be the resonant frequency, where the power will be maximum. But now they've given information like this, that see what is happening when frequency is varied gradually in one direction from F1 to F2, the power is found to be maximum at F1. Okay. When the frequency is in the other direction from F1 to F3, the power is same at F1 and F3. Okay. So that means here is probably something like this. F1 to F2, you're going in one direction. So let's say this is F1. This is F2. But F1 to F3, you're going in the opposite direction. So the power factor is the same. So if at F1 and F3, the power factor is same, that means the value of XL minus XC whole square is the same. Okay, so that means you have that kind of relation now. So you have the relation that resonant frequency is 1 upon 2 pi root LC. Okay, you have here F1 is equal to F3. So that means omega 1L minus 1 by omega 1C is equal to 1 by omega 2C minus omega 2L. Yeah, P1 is equal to P3. That's given now. That's why. So P1 is equal to P3 means basically now for P1 and P3, this is the situation. For this is your, this is one phasor and this is the other phasor. This is the relation. Okay. So that's why you got this. That at this now, the basically XL minus XC whole square for F1 is equal to XL minus XC whole square for F2. That's how you're getting this relation. So basically, whatever relation you will get in omega, same relation is in F. So from here you can understand. So understand, no? So just manipulate this in such a way that you can see the relationship between omega and 1 and omega 2 with respect to 1 by root LC. See that relationship? Same will be the relationship between. So can you give this a try and work it out now, Aditya? Okay. Okay, next let's look at this question. Just go through it once. Okay, so people, let's see what we'll do in this question is that you just solve this loop and solve this loop. Okay. So you will get this quite easily, no? You will see that all the values are given to you. So for the I2, it will be 200 root 2 by some z2, okay, into sine 100t plus some phi 2. Okay, so you can see that for this I21, okay, so now your xc so 50 root 3, okay, and your I1 similarly will be okay, that is millifarad, sorry, so there is a factor of 10 raised power minus of minus 3 here, so it will be 1000 by 50 root 3. This will be 1000 by 50 root 3, so this is 20 by root 3 ohms. So this is actually quite easy, this part now. This z2 will become 20 by root 3 whole square plus 20 square. So 40 by root 3. Yeah, there's no need to incorporate complex numbers. Now that is the thing. Like if you just simply solve like this now, and you can see your phi 2 is tan inverse of xc by this thing, xc by or minus of tan inverse of xc by r2. So that's going to be minus pi by 6. And similarly as z1, so there's no need to incorporate complex numbers in this. You just solve it as two sinusoidal currents and get the values of phi 1, phi 2 and get the corresponding values of these amplitudes and compare them. So similarly your XL you can see is 100 into root 3 by 10, that's 10 root 3. So this will be and R1 is 10 root 2. Okay. So 10 root 5, that is your Z1. And your phi 1 will become tan inverse of root 2 by root 3 or whatever, root 3 by root 2. Okay, so once you got this phi 1, phi 2 and these two amplitudes, now you can just substitute that the current through, oh sorry, I've taken the value of R1 is wrong. R1 is 10. That's what I thought, that we're getting a very odd value here. So this will just become 20 now. This will just be 20 ohms, and phi 1 will just be tan inverse root 3. So it will be pi by 3. Okay, so this is very easy. This phase term is pi by 3 and this term is 20. And this phase term is minus pi by 6 and this term is 40 by root 3 or whatever. Now from that you can easily, so at the instant when this current becomes 10 root 2, you can see this is 20 now. So this is 10 root 2. That means this term is 1. So sine 100t plus pi by 3 is equal to 1. That means 100t is equal to pi by 6. So put that as pi by 6 here. So this term will become 0 because this is minus pi by 6. So you can see that I2 will be 0. So I think the answer should be I2 will be 0. Is that the correct answer? Yeah, Devesh, I have received your doubts, but there are doubts of other people also pending. I have to go in serial order. So I will be picking up the remaining doubts in the next lecture. Okay. So I'll send some of you the hints for some of the doubts and other questions I'll be taking up in the class. You also have another physics class with Hemant sir also, so you can keep doing your doubts. All the classes are now doubts classes only. Okay, people, so that's it for today's lecture. Okay, wish you all the best. Keep sending your doubts. I will send you some hints, etc. Okay, Devesh, I will help you out by Sunday for that.